today's goal of this lecture. Today I will see connectedness of topological space and some conditions for connectedness. This is today's goal of this lecture. Today I will see what is the definition of connectedness, when to topological space connectedness, what is some condition on connectedness. This part is very important for any competitive exam, also for higher study. So please pay attention on whole video. Okay, let's see at first what is the definition of connectedness. Definition of connectedness is, let X be topological space, then a separation of X is pair of disjoint open set A and B. This is pair of disjoint open set A and B such that A intersection B equal to X and the topological space X equal to A union B. Then this A and B is separation of X. This is called disconnected set, and A space X is connected if there does not exist any separation. Okay, I hope my all viewers have understood what is the definition of connectedness. When there exists no separation, then this space is called connected. And there exists a nice remark. If A and B is a separation of X, then A complement equal to B. Similarly, B complement equal to A. Then both A and B are cloven of X. I hope my all viewers have understood. That means when the set is disconnected, then A and B both open and close in the space X. And when a topological space X is connected, then the condition, the only subset that are both open and closed are phi and X. I hope my all viewers have understood. In connected space, only subspace which are both open and closed, these are only phi and X. Okay, I will see some example. Easy. Consider X equal to 1, 2, 3 and consider the topology tau 1 equal to phi x1 and consider the topology tau 2 equal to phi x1, 2, 3. Notice for tau 1, here the non-empty open set are X and 1, and notice X intersection 1 is not equal to phi. So the topological space tau 1 is connected. And for tau 2, here non-empty open set are x, 1 and 2, 3. This is the non-empty open set, and the open set x1, x2, 3 are not disjoint open set. Disjoint open set are 1 and 2, 3. And intersection of 1 and 2, 3 is equal to phi. So tau 2 is disconnected topological space. I hope my all viewers have understood. And tau 1 is connected topological space. Okay. And in R, any interval is connected. This proof is very easy type proof, and any standard book this proof has given. Since any interval in R are connected, so R is connected set. I will prove this. Why R is connected set? Why R is connected? I will prove it by contradiction. Consider let R is disconnected. I will prove it by contradiction. Then R equal to U intersection V, where U and V are disjoint open set. Let A belongs to U and B belongs to V, and A less than B. Then close interval AB equal to close interval AB intersection U union close interval AB intersection V. Okay, both set are non-empty. Sorry, here I have done one thing wrong. Here this would be close interval AB. Both sets are non-empty as A belongs to close interval AB intersection U and B belongs to close interval AB intersection V. This shows that close interval AB is disconnected, which is contradiction. Because close interval AB, I have shown few minutes ago, in R every interval are connected set. So R is always connected set. Okay? Oh well. That means the set R is a connected set and every interval in R is a connected set. Separation in subspace topology, and what is the connectedness in subspace topology? This is if Y is a subspace of S, if Y is a subspace of X, then A separation of Y is a pair of disjoint non-empty set A and B whose union is Y. If neither of which contain a limit point of other. If this is separation of X, then neither of which contain a limit point of other. And the space Y is connected if there exists no separation of Y. Since A contains low limit points of B or B contains low limit point of A, that means when the space is disconnected in subspace, then in subspace topology, then A closure intersection B would be phi and A intersection B closure, this would be phi. Proof is such type, suppose A and B are forms a separation of Y. Then A is both. Since A and B are both separation, that means A is both open and close in Y. And the closure of A in Y is the set A closure intersection Y. And since A is closed, that imply A equal to A closure intersection Y or A closure intersection B equal to phi. Since A closure is the union of A and its limit point, so B contains no limit point. Limit points of A. Similarly, A contains no limit point of B. Limit point of B. That means the space Y is connected if there exists no separation in such type. Okay, I hope my all viewers have understood. Example, y equal to -1 0 close interval -1 open interval 0 union open interval 0 close interval 1. This is obviously subset of R. Now consider A equal to close interval -1 open interval 0 and B equal to 0 close interval 1. And these A and B are open in Y because A equal to -2, 0 intersection Y and B equal to 0, 2 intersection Y. So A, B are open set in Y and notice A intersection B equal to phi and non-empty. So A, B are separation of Y. So this set Y is not connected set. Also notice here A closer equal to -1 close interval 0 and B closer equal to 0 1, and A closer intersect with B is equal to 5. A closer intersect with B equal to 5. Similarly, B closer intersect with A equal to 5. So A, B are separation of Y, so this is not connected set. Second, if Y equal to close interval -1 0 union open interval 0 closed 1, determined Y is connected. Y is connected because here A equal to close interval -1 0 and B equal to open interval 0 1. This is not separation of Y because as A closer intersection B equal to 5 and A intersection B closer equal to singleton set 0. So this set is connected set. Okay, I hope my all viewers have understood. Well, next I will see set of rational number is not connected in subspace topology. Consider Y equal to Q and X equal to R and Q subset of R. Consider A equal to Q intersection -infinity square root of 2 and B equal to Q intersection square root of 2 into infinity. Obviously this is the non-empty open set in Y and A intersection B equal to 5. AB separation of Y. AB is separation of Y. Since AB is a separation of Y, so Q is disconnected in real line. Similarly, R intersection Q is not connected in R. Next, X equal to R and tau is finite complement topology. In finite complement topology, R is connected. Why? At first consider this is not connected, then set A and B be the separation of R. Then A complement equal to B, which must be finite. Similarly, B complement equal to A, this is must be finite. And R equal to A union B. And union of two finite set always be finite. So R be finite, this is with a contradiction. Because R is infinite set. So this is not B separation, this is connected set. That means in cofinite topology, real number in cofinite topology is connected set. I hope my all viewers have understood this is okay. Oh, now I will say the space RL is connected. Why? Minus infinity to A and A to close interval A to infinity are open in RL. Why this is open in RL? Because we can write minus infinity A equal to union of close interval minus NA and close interval A infinity. We can write this as union of close interval A comma n plus 1. And this is actually, these are union of open set. Also we can write these are union of open set. So we all of us know union of open set is always open. So these are open in RL. And we all of us know minus infinity A and close interval A infinity are open in RL. And minus infinity to A intersection A to infinity, this is a disjoint open set because these are fine. And minus infinity A union closed A infinity, this is equal to whole RL. So the space RL is connected. This is the wrong. The space RL is actually disconnected. RL is not connected because it can be expressed as two non-empty disjoint open set. Okay? I will stop here. In my next video, I will discuss more concept about connectedness. Actually, connectedness, this topic is very important for higher study. Okay? See you soon, stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.